Alright, so I wanted to make a quick video for you guys on exponent rules. My name's Garrett Evans, by the way. I do tutoring for math and physics. If you're ever interested in getting help on either of those topics, please look me up. Exponent rules. So, what is exponentiation? What does it mean to raise something to an exponent? Well, when we do exponentiation, what we usually do is we take a number and we put a smaller number next to the number, kind of up and to the top right of it, as a little bit of a superscript, you might call that. What does that mean? The meaning is how whatever this number is that's up here at the top right, we're going to multiply the main number by itself that many times. So for example, if we're doing 2 to the power 3, as we have here, we're taking 3 2's and we're multiplying them by each other. What's that going to give us? Obviously, 2 times 2 times 2. 2 times 2 is 4. 4 times 2, that's the third 2, that's going to be 8. So this number here is going to be 8. Terminology. This number, the 2, is called the base. The 3, or the number we're raising to the power of, is called the power, or the exponent. We can do other things with bases and exponents. For example, we can do 3 to the power 3. If we do 3 to the power 3, that's going to be 3 3's multiplied. 3 times 3, that would be 9. 9 times 3, that would be 27. 4 to the power 2, that's 2 4's multiplied. It's also called 4 squared. 4 times 4, that's 16. 5 to the power 4, we could do that one. That's going to be 4 5's multiplied. 5 times 5 is 25. 25 times 5, again, would be 125. And then 125 times 5, once more, that's going to bring us up to 625. A nice little notation to use in general when we're raising something to a power. Maybe we don't know what the power is, but we want to express it as a variable. We're writing a to the power n. A is our base, n is our exponent. We're going to write this out kind of in this abstract way. We're going to write a string of a's with dot dot dots in the middle, meaning that something goes in there and we're not going to write out all of what it is, and we're going to put this little n over the top here to indicate, okay, well, there's n total a's in here that are being multiplied. And that's what a to the power n is. That little way of writing it is going to be useful when we start trying to reason about general expressions involving bases being raised to powers. Okay. The first exponent rule I'd like to talk about is power of a product. What happens when we take two numbers being multiplied together and then we raise that grouping of numbers as a unit to a power? Well, just from the definition of what exponentiation is, it means we're going to take that parentheses and we're going to multiply it by itself. How many times? 4 times. So 2 times 3 is 1 parentheses. 2 times 3, that's the second, third, and fourth. But what have we got here? We've got 4 total 2's. And we've got 4 total 3's, all being multiplied. But order does not matter when we're multiplying numbers together. Therefore, we can reorder these any way we want. We could put the 4 2's together in the front, and then we could put the 4 3's together as a string at the end. We're completely free to do that. And once we do that, we recognize that, hey, 4 2's multiplied together, that's exactly what we've been talking about. 4 2's multiplied together, that's exactly 2 to the power 4. Same thing, 4 3's multiplied together, that's exactly 3 to the power 4. So we can express 2 times 3 to the power 4, that's just 2 to the 4, times 3 to the 4. So the effect is this 4, this power, has distributed across the product. That's very similar to what you get when you multiply a parenthesis that contains a sum of two terms times something sitting on the outside of those terms. That something will distribute to the two terms. This is similar here. Now we're distributing an exponent to a product of things. That's allowed. Why is it allowed? It's allowed because exactly this logic right here. Let's verify. 2 times 3 to the power 4. 2 times 3 is 6. So that's going to be 6 to the 4. 2 to the 4, that's 2 times 2, which would be 4, times another 2 is 18. 4 2's is going to bring us up to 16. If we do 3 to the power 4, 3 times 3, that's 9, times another 3 is 27. 27 times 3, that's going to bring us up to 81. So 2 to the 4 times 2 to the 4, that's 16 times 81. 6 to the power 4. I am not going to do that out using math because it's too difficult. So I'm going to put it into my calculator. Actually, I already did put it in my calculator. And you can do the same and discover that the answer is 1296. 16 times 81, though, if you put that into the calculator, you're going to get the same number, 1296. So we verified that indeed the formula works. Of course, we knew it had to work because all of our logic up here is totally sound. That pattern is going to work regardless of what you put into the parentheses and regardless of what the power is. Why is it going to work? Because you're going to be whatever your power is, how many copies of A times B you're going to be taking, you're going to be able to reorder the A's and B's that appear when you multiply them all together. And at the end of the day, you're going to have n A's and you're going to have n B's all multiplied. That's the same as A to the n times B to the n. So that's a general thing that you can use. Not just for 2 and 3 and 4, but for anything that you want. You can do a similar thing with quotients or fractions. You can take a power of a quotient. Let's think about how that's going to work. And for this, we're going to use that kind of abstract way of writing out what something to the nth power is. A over B to the nth power. To get that, we're going to take n copies of A over B. That's what we're indicating here with the dot dot dots and the n that appears up here. We are going to take those n copies of A over B and we're going to multiply them all together. That's the definition of raising something to the nth power. But when we are multiplying fractions, the job that we have to do to perform that is multiply across top and multiply across bottom. So what we're going to wind up with is n copies of A on the top and n copies of B on the bottom. But guess what? According to our definition of exponentiation, that's the same thing as A to the n copies of A, that's A to the n copies of B, all multiplied, that's B to the n. So we've got it again. A over B raised to the power n, that n just comes into the A and to the B. And it looks exactly like this. A to the n divided by B to the n. It makes it simple. Let's think about an example of that. 2 over 3 raised to the power 4. According to our formula and our logic that we've worked out right here, that 4 is going to come down to the 2 and to the 3. So we're going to be able to write it as 2 to the 4 divided by 3 to the 4. 2 to the 4, as we said on the last board, that's 2 times 2 is 4. 4 times 2 is 8. 8 times 2, that's 4 2s, is going to be our 16. That's up top. 3 to the power 4. 3 times 3 is 9. 9 times 3, 27. 27 times 3, that's bringing us up to 81. So we're going to have 16 divided by 81. Okay? So that's what the formula says. 2 divided by 3 raised to the power 4. That should be equal to 16 over 81. Let's check it. 0.6667, that's an approximation of 2 over 3. If we raise it to the 4th power using the calculator, we're going to get 0.1975. If we do the same thing with our fraction, we're going to get the same number on the calculator. 16 divided by 81, 0.1975. So, as you can see, the formula works quite well. Power of a power. This is the last rule I'm going to go over with you guys for today. Just kind of trying to keep the video a bit short. Power of a power. What happens if we take a number that itself is a power and we raise it to another power? So we're doing 2 to the 3 here, and then we're going to raise that to the 2 power. Well, an easy way to get that would be just to figure out what 2 to the 3 is, and then multiply that by itself. But we're not going to do it that way, because we want to get the general pattern. 2 to the 3 raised to the 2nd power. By definition, 2 to the 3 is 3 2's multiplied together. So we can write those out just like so. And we're squaring that, means we're going to take 2 copies of that string of 3 2's, and we're going to multiply them together, by definition. I'm going to write that out as a second row underneath the top row. And the reason I'm going to do that is because it makes it easier for us to figure out how many total 2's there are in the expression. How many are there? There's 3 2's across the top. There's 2 rows. That's giving us a total of 6 2's. 3 times 2, 6. 3 columns, 2 rows, 6 2's. So, what we've verified is that 2 to the 3 raised to the 2 is the same thing as 2 to the 3 times 2. That's 2 to the 6th power. Let's verify that. If we do it the easy way, we do 2 to the 3, that's 8. 8 raised to the 2, that's 8 times 8. 8 times 8 is 64. 2 to the 6, what's that? 2 times 2, 4. 4 times 2, 8. 8 times 2, 16. 16 times 2 is 32. That's 5 2's. So 6 2's would bring us up to 32 times 2. That's 64. And sure enough, 2 times 6, 2 to the power 6, that's the same thing as 2 to the 3 to the power 2. We see that the formula works. Let's talk about it in general. Anytime we've got an expression of this form, some base raised to a power n, and that has a unit being raised to a different power m, we can write out the a to the n as n a's, all multiplied as a string. That's going to be raised to the m still. To do raising to the power m, we're going to take m of those strings of n a's, and we're going to write them out as rows, just like this. M rows of n a's. And in doing so, it's going to build a giant table of a's with n a's across the top, that's n columns, and there's going to be m rows. That means the total number of a's in this giant table is going to be n times m. There's going to be n times m total a's being multiplied together. That means our power is a to the power. Our total power is n times n, and our expression is a to the power n times n. So what we've proved is that a to the n, in parentheses, raised to the power m, That's called a to the n times n. That's the power of a power rule. Okay, like I said, I wanted to keep this video short. There are more exponent rules than just these, but I'm going to stop it here, and maybe we'll come back and do some more in another video coming up at another time. Alright, thanks for watching!